Well, just before the break, not sure if you noticed it, but something nasty started to happen. So we've been going along with these streams and divorcing time in the programs from time in the computers, and all that divorcing got hidden inside the streams. And then at the very end, we saw that sometimes, in order to really take advantage of this method, you have to pull out other delays. You have to write some explicit delays that are not hidden inside that const stream. And I did a very simple example with differential equations, but if you have some very complicated system with all kinds of self-loops, it becomes very, very difficult to see where you need those delays. And if you leave them out by mistake, it becomes very, very difficult to see why the thing maybe isn't working. So that's kind of a mess, that by getting this power and allowing us to use delay, we end up with some very complicated programming sometimes, because it can't all be hidden inside those streams. Well, is there a way out of that? Yeah, there is a way out of that. We could change the language so that all procedures acted like const stream, so that every procedure automatically has an implicit delay around its arguments. And what would that mean? That would mean when you call a procedure, the arguments wouldn't get evaluated. Instead, they'd only be evaluated when you need them. So they might be passed off to some other procedure which wouldn't evaluate them either. So all these procedures would be passing promises around, and then finally, maybe when you finally got down to having to look at the value of something that was handed to a primitive operator, would you actually start calling in all those promises. If we did that, see, since everything would have a uniform delay, then you wouldn't have to write any explicit delays, because it would be automatically built into the way the language works. Or another way to say that, technically what I'm describing is what's called, if we did that, our language would be so-called normal order evaluation language versus what we've actually been working with, which is called applicative order. Versus applicative order evaluation. And remember the substitution model for applicative order. It says when you go and evaluate a combination, you find the values of all the pieces. Right? You evaluate the arguments, and then you substitute them in the body of the procedure. Normal order says, no, don't do that. What you do is effectively substitute in the body of the procedure, but instead of evaluating the arguments, you just put a promise to compute them there. Or another way to say that is you take the expressions for the arguments, if you like, and substitute them in the body of the procedure and go on. And never really simplify anything until you get down to a primitive operator. So that would be a normal order language. Well, why don't we do that? See, if we did, we'd get all the advantages of delayed evaluation with none of the mess. In fact, if we did that, and const was just a delayed procedure, that would make const the same as const stream. We wouldn't need streams at all, because lists would automatically be streams. That's how lists would behave. And all data structures would behave that way. Everything would behave that way. Right? You'd never really do any computation until you actually needed the answer. Right? And you wouldn't have to worry about all these explicit annoying delays. Well, why don't we do that? First of all, I should say people do that. There's some very, very beautiful languages. One of the very nicest is a language called Miranda, which is developed by David Turner at the University of Kent. And that's how this language works. It's a normal order language, and its data structures, which look like lists, are actually streams. And you write ordinary procedures in Miranda, and they do these prime things and these 8 queens things just without anything special. It's all built in there. But there's a price. Remember how we got here? We're decoupling time in the programs from time in the machines. And if we put delay, that sort of decouples it everywhere, not just in streams. Remember what we're trying to do. We're trying to think about programming as a way to specify processes. And if we give up too much time, our language becomes more elegant, but it becomes a little bit less expressive. There are certain distinctions that we can't draw. One of them, for instance, is iteration. Remember this old procedure, right? Iterative factorial that we looked at quite a long time ago. Right? Iterative factorial had a thing, and it said there was an internal procedure, and there was a state, which was a product, and a counter. And we iterate that going around the loop. And we said that was an iterative procedure because it didn't build up state. And the reason it didn't build up state is because this iter that's called is just passing these things around to itself. Or in the substitution model that you could see in the substitution model that Jerry did, that in an iterative procedure, that state doesn't have to grow. And in fact, we said it doesn't, so this is an iteration. But now think about this exact same text if we had a normal order language. What would happen is this would no longer be an iterative procedure. And if you really think about the details of the substitution model, which I'm not going to do here, this expression would grow. Why would it grow? It's because when iter calls itself, it calls itself with this product. If it's a normal order language, that multiplication is not going to get done. It's going to say, I'm going to call myself with a promise to compute this product. And now iter goes around again. And I'm going to call myself with a promise to compute this product where now one of the factors is a promise. And I call myself again. And if you write out the substitution model for that iterative process, you'll see exactly the same growth in state. All those promises that are getting remembered that have to get called in at the very end. So one of the disadvantages is that you can't really express iteration. Maybe that's a little theoretical reason why not. But in fact, people who are trying to write real operating systems in these languages are running into exactly these kinds of problems. Like it's perfectly possible to implement a text editor in languages like these, but after you work a while, you suddenly have 3 megabytes of stuff, which is, I guess they call them the dragging tail problem. People who are looking at these, of promises that sort of haven't been called in because you couldn't quite express an iteration. And one of the research questions in these kinds of languages are figuring out the right compiler technology to get rid of this so-called dragging tails. It's not simple. But there's another kind of more striking issue about why you just don't go ahead and make your language normal order. And the reason is that normal order evaluation and side effects just don't mix. They just don't go together very well. Somehow you can't, it's sort of, you can't simultaneously go around trying to model objects with local state and change, and at the same time do these normal order tricks of decoupling time. Let me just show you a really simple example, very, very simple. Suppose we had a normal order language, and I'm going to start out in this language. This is now normal order. I'm going to define x to be 0. It's just some variable, and I'll initialize. And now I'm going to define this little funny function, which is an identity function. And what it does, it keeps track of the last time you called it using x. So this is, all right, so the identity of n just returns n, but it sets x to be n. And now I'll find a little increment function. Right, so there's a very little simple scenario. Now imagine I'm interacting with this in a normal order language. And I type the following. I say, define y to be increment the identity function of 3. So y is going to be 4. Right. Now I say, what's x? Well, x should have been the value that was remembered last when I called the identity function. So you'd expect to say, well, x is 3 at this point. But it's not. Because when I defined here, y here, what I really defined y to be increment of a promise to do this thing. So I didn't look at y, so that identity function didn't get run. So if I type in this definition and look at x, I'm going to get 0. Now if I go look at y and say, what's y? Say y is 4. Looking at y, that very act of looking at y, caused the identity function to be run. And now x will get remembered as 3. So here x will be 0, here x will be 3. That's a tiny little simple scenario. But you can see what kind of a mess that's going to make for debugging interactive programs when you have normal order evaluation. It's very confusing. But it's very confusing for a very deep reason, which is that the whole idea of putting in delays is that you throw away time. That's why we can have these infinite processes. Since we've thrown away time, we don't have to wait for them to run. Right? We decouple the order of events in the computer from what we write in our programs. But when we talk about state and set and change, that's exactly what we do want control of. So it's almost as if there's this fundamental mental contradiction in what you want. And that brings us back to these sort of philosophical mutterings about what is it that you're trying to model and how do you look at the world. Or sometimes this is called the debate over functional programming. Now, a so-called purely functional language is one that just doesn't have any side effects. Since you have no side effects, there's no assignment operator, so there are no terrible consequences of it. You can use a substitution-like thing. Programs really are like mathematics and not like models in the real world, not like objects in the real world. There are a lot of wonderful things about functional languages. Since there's no time, you never have any synchronization problems. And if you want to put something into a parallel algorithm, you can run the pieces of that parallel process in any way you want. Right? And there's just never any synchronization to worry about. And it's a very congenial environment for doing this. The price is you give up assignment. So an advocate of a functional language would say, gee, that's just a tiny price to pay. You probably shouldn't use assignment most of the time anyway. And if you just give up assignment, you can be in this much nicer world than this place with objects. Well, what's the rejoinder to that? Remember how we got into this mess. All right, we started trying to model things that had local state. So remember Jerry's random number generator. There was this random number generator that had some little state in it to compute the next random number and the next random number and the next random number. And we wanted to hide that state away from the Cesaro compute pi process. And that's why we needed set. We wanted to package that state in modularly. Well, a functional programming person would say, well, you're just all wet. I mean, you can write a perfectly good modular program. It's just you're thinking about modularity wrong. Right? You're hung up in this next random number and the next random number and the next random number. Why don't you just say, let's write a program, let's write an enumerator, which just generates an infinite stream of random numbers. Right? And we can sort of have that stream all at once. And that's going to be our source of random numbers. And then if you like, you can put that through some sort of processor, which is, I don't know, a Cesaro test. And that can do what it wants. And what would come out of there would be a stream of successive approximations to pi. So as we looked further down this stream, we'd tug on this Cesaro thing, and it would pull out more and more random numbers. And the further and further we look down the stream, the better an approximation we get to pi. And it would do exactly the same as the other computation, except we're thinking about the modularity different. We're saying, imagine we had all those infinite stream of random numbers all at once. And you can see the details of this procedure in the book. Right. Similarly, there are other things that we tend to get locked into on this one and that one and the next one and the next one, which don't have to be that way. Like you might think about a banking system. Right, just a very simple idea. Imagine we have a program that sort of represents a bank account. Right. The bank account might have in it, if we looked at this in a sort of message passing view of the world, we'd say the bank account is an object that has some local state in there, which is the balance, say. And a user using the system comes and sends a transaction request. So the user sends a transaction request, like deposit some money, and the bank account maybe, let's say the bank account always responds with what the current balance is. Right, so the user says, let's deposit some money, and the bank account sends back a message, which is the balance. And the user says, deposit some more, and the bank account sends back a message. And just like the random number generator, you'd say, gee, we would like to use set. We'd like to have balance be a piece of local state inside this bank account because we want to separate the state of the user from the state of the bank account. Well, that's the message processing view. There's a stream view of that thing, which does the same thing without any set or side effects. And the idea is, again, we don't think about anything having local state. We think about the bank account as something that's going to process a stream of transaction requests. So think about this bank account not as something that goes message by message, but something that takes in a stream of transaction requests, like maybe successive deposit amounts. Well, I don't know, 1, 2, 2, 4. Those might be successive amounts to deposit. And then coming out of it is the successive balances, 1, 3, 5, 9. So we think of the bank account not as something that has state, but something that acts sort of on the infinite stream of requests. But remember, we've thrown away time. So what we can do is, if the user's here, we can have this infinite stream of requests being generated one at a time, coming from the user. And this transaction stream coming back on a printer being printed one at a time. And if we drew a little line here, right there, to the user couldn't tell that this system doesn't have state. It looks just like the other one, but there's no state in there. And by the way, just to show you, here's an actual implementation of this. We'll call it make deposit account because you can only deposit. It takes an initial balance and then a stream of deposits you might make. And it's, what is it? Well, it's just const stream of the balance onto make a new account stream, whose initial balance is the old balance plus the first thing in the deposit stream, and whose rest, right, and whose make deposit account works on the rest of, which is the tail of the deposit stream. So there's sort of a very typical message passing object-oriented thing that's done without side effects at all. There are very many things you can do this way. Well, can you do everything without assignment? Did everybody go over to purely functional languages? Well, you don't know, but there seem to be places where purely functional programming breaks down. Where it starts hurting is when you have things like this, but you also mix it up with the other things that we had to worry about, which are objects and sharing, and two independent agents being the same. So one very typical one is, suppose you want to extend this bank account. So here's a bank account. It's going to take in bank accounts take in a stream of transaction requests and put out streams of, say, balances or responses to that. But suppose you want to model the fact that this is a joint bank account between two independent people. Right. So suppose, suppose there are two people, say Bill and Dave, who have a joint bank account. How would you model this? Well, Bill puts out a stream of transaction requests, and Dave puts out a stream of transaction requests, and somehow they have to merge into this bank account. So what you might do is write a little stream processing thing called merge, which sort of takes these, merges them together, produces a single stream for the bank account. Now they're both talking to the same bank account. That's all great, but how do you write merge? See, what's this procedure merge? You want to do something that's reasonable. Your first guess might be to say, well, we'll take alternate requests from Bill and Dave. See, but what happens if, suddenly in the middle of this thing, Dave goes away on vacation for 2 years? Right, then Bill sort of is stuck. So what you want to do is, well, it's hard to describe. What you want to do is what people call fair merge. And the idea of fair merge is it sort of should do them alternately, but if there's nothing waiting here, it should take one twice. Notice I can't even say that without talking about time. So one of the other active research areas in functional languages is inventing little things like fair merge and maybe some others, which will take the places where I used to need side effects and objects and sort of hide them away in some very well-defined modules of the system, so that all the problems of assignment don't sort of leak out all over the system, but are captured in some fairly well-understood things. Okay. More generally, I think what you're seeing is that we're running across what I think is a very basic problem in computer science, which is how to define languages that somehow can talk about delayed evaluation, but also be able to reflect this view that there are objects in the world. How do we somehow get both? And I think that's a very hard problem, and it may be that it's a very hard problem that has almost nothing to do with computer science, that it really is a problem having to do with two very incompatible ways of looking at the world. Okay, questions?
You mentioned earlier that once you introduce assignment, the general rule for using the substitution model is you can't. Unless you're very careful, you can't.
Right.
Is there a set of techniques or a set of guidelines for localizing the effects of assignment so that the very careful becomes defined?
I don't know. Let me think. Well, certainly there was an assignment inside MemoProc, but that was sort of hidden away. It ended up not making any difference. Part of the reason for that is once this thing triggered that it had run and gotten an answer, that answer will never change. So that was sort of a one-time assignment. So one very general thing you can do is if you only do what's called one-time assignment, you never change anything, then you can do better. One of the problems in this merge thing, people have, see if this is right. I think it's true that with fair merge, with just fair merge, you can begin effectively simulating assignment in the rest of the language. It seems like anything you do to go outside, I'm not quite sure that's true for fair merge, but it's true of a little bit more general things that people have been doing. So it might be that any little bit you put in, suddenly, if they allow you to build arbitrary stuff, it's almost as bad as having assignment altogether. But that's an area that people are thinking about now.
I guess I don't see the problem here with merge if in a sense, if I call Bill, if Bill's a procedure, then Bill is going to increment the bank account or build the list. It's going to put in the next element. If I call Dave twice in a row, that will do that. I'm not sure where fair merge has to be involved.
The problem is, imagine these really as people. See, here I have a user who's sitting interacting with this bank account. Put in a request, get an answer, put in a request, get an answer. But if the only way I can process requests is to alternate them from two people.
Why don't you alternate them?
Why don't I? Because this guy might think of them as real people. Right? This guy might go away for a year. And you're sitting here at the bank account window. And you can't put in two requests because it's waiting for this guy.
Why does it have to be waiting for one?
Because it's trying to compute a function. I have to define a function. Another way to say that is the answer to what comes out of this merge box is not a function of what goes in. Because, see, what would the function be? Suppose he puts in 1, 1, 1, 1, and he puts in 2, 2, 2, 2. What's the answer supposed to be? It's not good enough to say it's 1, 2, 1, 2, 1, 2.
I understand, but right? When Bill puts in 1, 1 goes in. When Dave puts in 2 twice, 2 goes in twice. When Bill puts in,
right.
Why can't it be hooked to the time of the input, the actual procedural?
Because I don't have time. See, all I can say is I want to define a function. I don't have time. Right? There's no concept of it's going to alternate, except if nobody's there, it's going to wait a while for him. Right? It's just going to say, I have the stream of requests, the timeless infinite streams of all the requests that Dave would have made. Right? And the timeless infinite stream of all the requests Bill would have made, and I want to operate on them. See, that's how this bank account is working. And the problem is that these poor people who are sitting at the bank account windows have the misfortune to exist in time. Right? They don't see their infinite stream of all the requests they would have ever made. They're waiting now and they want an answer. Right? So if you're sitting there, if this is the screen operation on some time-sharing system and it's working functionally, you want an answer then when you type the character. You don't want it to have to wait for everybody in the whole system to have typed one character before it can get around to service you. So that's the problem. It's the fact that people live in time, apparently. If they didn't, it wouldn't be a problem.
I'm afraid I missed the point of having no time in this banking transaction. Isn't time very important? For instance, the sequence of events. If Dave takes out $100 and
Yes.
the timing sequence should be
That's right.
important. How do you treat transactions as streams?
Well, that's the thing I'm saying. This is an example where you can't. You can't. The point is, what comes out of here is simply not a function of the stream going in here and the stream going in here. It's a function of the stream going in here and the stream going in here, and some kind of information about time, which is precisely what a normal order language won't let you say.
In order to bring this back into a more functional perspective, could we just explicitly timestamp all the inputs from Bill and Dave and define fair merge to just be the sort on those timestamps?
Yeah, you could do that. You can do that sort of thing. Another thing you could say is imagine that really what this function is that it does a read every microsecond. And then if there's none there, that's considered an empty one. That's about equivalent to what you said. And yes, you can do that, but that's a kludge. So you're not. It's not quite only implementation we're worried about. We're worried about expressive power in the language, and what we're running across is a real mismatch between what we can say easily and what we'd like to say.
It sounds like where we're getting hung up with that is the fact that it expects one input from both Bill and Dave at the same time.
It's not quite one, but it's anything you define. So you can say Dave can go twice as often, but it's anything you predefine is not the right thing. Right? You can't decide it's some particular function of their input requests. Worse yet, there are things that even merge can't do. One thing you might want to do that's even more general is suddenly you add somebody else to this bank account system. You go and you add John to this bank account system. And now there's yet another stream that's going to come into the picture at some time which you haven't pre-specified. So that's something even fair merge can't do, and there are things called, managers or something. That's a generalization of fair merge to allow that. There's a whole sort of research discipline saying how far can you push this functional perspective by adding more and more mechanism. And then how far does that go before the whole thing breaks down and you might have well been using set anyway.
We need to set them up on automatic deposit.
No. Okay, thank you.